So let us start with what are the differences between cantilever and counterfort retaining walls, how they are different structurally. What you should understand from these two structures, I'll show you here. Now you observe this. This is a cantilever retaining wall. See how to differentiate between these two. Observe here. See this, when you see this difference in thicknesses at the base and at the top of the stem, you can see there are three components here. In case of a cantilever retaining wall, now I'll draw this figure of counterfort retaining wall. Now you observe this, how they are different, and how to design them separately. The basic difference when you see here is, the first difference is, when you look at the stem, the thickness is not uniform. In case of cantilever retaining wall, thickness at the base is more, at the top it is actually theoretically 0 is there, but some practical difficulties will be there at the side. Some 200 mm to 250 mm can be adjusted here. The bottom thickness depends upon the bending moment criteria. Okay. Now when you look at this particular counterfort retaining wall, I'll draw one more line here to show what is the counterfort, what it does exactly. From the side view, it looks like this. And remember, Earth is this side. Earth is here. This is all Earth. It means the Earth pressure is acting like this. So when I say heel of the section, now you try to compare these two and understand, so that it will be easy for you to design whether it is a cantilever or counterfort. So the basic difference when you look at the sketch is, thickness is not uniform in case of cantilever retaining wall, whereas in case of counterfort, the stem thickness will not change from top to bottom, it remains the same. This is one difference. Second one is, you are finding one more extra component which is called as counterfort. How this counterfort is working? What is the, now look at this counterfort here. Okay. Now see this one. Now you observe this figure. What is the purpose of a counterfort? Why it is provided? There is one question. When do we go for counterfort or cantilever retaining walls? Under what circumstances this is preferred over this? Because steel requirement for counterfort is very huge. Counterfort is costlier than cantilever retaining wall, even in terms of design as well as materials. Design is also a little bit lengthy, and steel requirement is very high when it is compared with cantilever retaining wall. For smaller depths, up to 5 meter or something like that, I can go for 5 to 6 meter also. I will go for cantilever retaining wall. If it is 5 meter or if it is 8 meters, if this height is more, height to be retained, if the height of earth to be retained is more, usually uh, counterfort is preferred. Counterfort is preferred. That does not mean that if the height is less, if the client says, even though the height is only 5 meters, but still I want counterfort only, means you have to design counterfort for that height also. But for smaller heights, it is uneconomical. Are you getting my point? If the height is less, let us say 5 meters, if somebody designs for 5 meter, both earth to be retained, height of earth to be retained is 5 meters, and if you're asked to design both, when the height to be retained is 5 meter, you will find that the counterfort retaining wall is very uneconomical. Counterfort is costlier than cantilever if the height is 5 meters. If the height is 7 meters, it is better to go for counterfort retaining walls. It depends upon the clients also sometimes. You may have to design counterfort for 5 meters also, but generally you should understand it will be costly, it will be uneconomical to design counterfort for a height of 5 meters. So in the examination, you have to be very much clear whether the problem is on counterfort or cantilever retaining wall. Now I'll show you how it is different structurally. Structurally, what is the difference between these two? When you look at this particular cantilever retaining wall, you will find that there are three components. All are fixed at the same junction. All these are fixed at the same junction. Now I'll show you here. All these are fixed at the same junction. That is why it is called as cantilever retaining wall. I'll draw an approximate circle like this here. Now you can see this. See these three components. One is stem, one more is heel, one more is toe. Okay, just like a human, our legs, you can say legs. If you see the legs, heel is backside, toe is front side. So heel is going to carry the weight of the earth, and stem will be subjected to horizontal earth pressure. Stem is subjected to horizontal earth pressure. Then heel is heel has to carry the weight of the backfill. This is, we call it as a backfill here. Whatever earth to be retained is backfill. So the backfill weight is transferred to heel. Okay, and toe is like this. Now, why this is called as a cantilever retaining wall? Because stem, heel, and toe all are cantilever slabs fixed at this junction. Whatever circle I have shown here, in this junction, all three are connected, and this junction is the fixed end, and the ends are free ends of these three components. You can see this one here. In case of a cantilever, this is the free end of stem, this is the free end of toe, this is the free end of heel, and all these three components are fixed at their junction. Okay, so this is why we call it as a cantilever retaining wall. Now here, how to design any RCC member, you know it very well. Here these are three slabs are there, that's all. One is a vertical slab, which is stem. Two are horizontal slabs. Now the bending takes place. Now you should see how because see, whenever we calculate steel for bending moment, mu. So for example, mu by bd square is calculated, corresponding steel, that is SP16 table is referred. We are going to find PT. From PT, I am going to find AST value, or any formula you can use. But basically, steel depends upon the bending moment mu only. Now for that one, you should understand how the bending is taking place in these three components, how it bends actually. Once you know that these are all cantilevers, the formula is WL square by 2. But how to find the WL square by 2 if at all it is UDL or whether it is uh, trapezoidal UDL is there or what? So either there will be trapezoidal UDL or there will be rectangular UDL. Whatever we study uniform distributed load, that is different. That is there. But in case of cantilever retaining wall, trapezoidal UDL will be there. You have to split it into UDL as well as triangular load. That I will show you. Once you know that one, the design becomes very simple. Absolutely nothing is there in this problem except stability analysis. Stability analysis is not related to RCC subject. Stability analysis is common to irrigation engineering also. Whatever dams you study stability analysis, here in case of dams something extra is there, but here basic stability analysis, whether it is a dam or a retaining wall, it remains the same. Overturning, sliding and crushing of the structure. Now I'll show you that one. Now the question here is, first of all, when you try to design a member, structurally how it behaves, whether it is a cantilever or a simply supported or a continuous beam or a slab or a cantilever slab or a simply supported slab, or is it an indeterminate structure? So you have to understand that one first, then how it's going to bend. What are the forces acting on it and how it is going to bend as a result of those forces. That I will show you in case of cantilever retaining wall. Observe this. Once you understand that, it design becomes very simple actually. I'll show you that one. Observe this figure. Just observe this. I'll draw a line diagram. This is I'll call this as a stem. Two lines I have shown for a stem. Then I'll draw one horizontal line like this. Again, I'll show small thickness, very small thickness. Now, this is your bottom thickness can be more than top since it is a cantilever. Let us not worry about that. Presently, one rectangle is like this, one more rectangle is like this, horizontal and vertical rectangles. I told you that. See, I told you that this is a cantilever retaining wall. It means all these are fixed here. At the junction, these three are fixed and they are free at the other end. Now the force acts like this. Force act like this. Since it is fixed at the base, free at the other end, it is going to bend like this. Simply the way you can see the whatever you have studied in the case of strength of material any subject, there what you have studied, this is a cantilever slab. It is going to bend like this. Same thing has happened here also, like this. Because this is a cantilever vertical slab. It is a vertical cantilever slab subjected to horizontal force. It bends like this. Only thing is that you have to find out this is a triangular load will be there. This load will not be UDL like this. It will be a triangular load. That is, you can see this here. This is a triangular load. Because earth pressure at the top, it depends upon the depth. As the depth increases, the earth pressure is also increasing. So at the top, if the top surface is in line with the top surface, it is horizontal backfill. I call it as horizontal backfill. If the backfill is like this, the earth can be like this also. It is surcharge or inclined backfill. So we are going to concentrate only horizontal backfill type of a problem in which this will be the triangular pressure. Means indirectly what I'm trying to say is the stem is subjected to triangular UDL, triangular load like this. it means maximum moment will be there at the junction. That is why thickness at the base is maximum. Since bending moment is maximum at the base, thickness requirement will be maximum at the base. It is 0 at the top. It means thickness can be 0 theoretically, but some practical reasons are there. I have to embed the steel inside, some cover is required, some maintenance issues will be there. For that one, theoretically, even if it is 0, I have to provide some thickness at the top. Bottom thickness is related to bending moment considerations. Since bending moment is very high at the base, thickness is relatively high. So this is how this stem is behaving in case of cantilever retaining wall. Now what will happen to this one? What will happen to the heel? Observe here. It is also a cantilever fixed at this point. All these are fixed at the same point. Our assumption is this is the fixed end. From fixed point only, all these are going to bend depending upon the net pressure acting on the particular member, heel or toe or stem. So what will happen uh, in case of heel? Observe this. Heel is going to bend like this. It is also cantilever. It bends like this. Why it bends like this? Because it is carrying this weight of the pressure, weight of the earth. There will be some net upward pressure. You have to find out the net weight on this net pressure, because net upward pressure subjected to it is, see, this entire retaining wall is subjected to upward pressure because it is resting on hard strata. For equilibrium, it has to see why it remains here only. Why it remains here? Why it is not going inside? Because earth is acting pressure now. Whatever strata is there, hard strata, it is going to act pressure in the upward direction. That is why the equilibrium is maintained. When I say it is not, why not it is sinking down? Why it remains there only? Means there has to be some force which is acting upwards so that the equilibrium is maintained. It is not going down. So this is what we call it as net upward pressure. Net upward pressure is responsible for keeping the retaining wall at the same position wherever it is in this position. It remains here because of the net upward pressure. In this way, the equilibrium is maintained. Now, I am telling you that it is going to bend like this. It is a cantilever fixed at junction, it bends like this. It is because earth, whatever weight of the earth and weight of this heel is becoming more than the net upward pressure. The net pressure is downwards now. So it bends like this. But here what happens? There is no earth. On the other side, if you look at this particular toe, we are not going to consider earth this side. Now what will happen is only net upward pressure is acting now. It is going to it is going to bend up like this. Now see the where is the compression fiber and tension fiber, you have to see. Okay. Now it bends like this. Now simply if I ask you to draw a figure showing in case of a cantilever, if I tell you to show how the bending shape you can see here. Basic things if you understand, the complicated things will become easier for you. Observe here. Now this is what is your this one. Actually shape after bending will be this one, this one, this one. In this way, the components, all these are cantilever slabs, they bend like this. Which means if you draw the thickness here like this, if you draw the thickness like this, again if you draw the thickness like this, you should understand the position of reinforcement. Now, which is a tension fiber, which is a compression fiber, you should understand. Then only you will be able to understand the positioning of steel. What I mean to say here is whether now my question is whether this is main steel green color, or if I ask you whether this is main steel red color. The question is whether Green is main reinforcement or red is main reinforcement? The answer is here. The answer, if you want to answer this question, it is here. You can see this this layer this layer is compressed. This layer is this layer is compressed. This layer is elongated. It means near to the backfill, I have to provide main reinforcement. Green is main steel. Because the way it bends, there is elongation in this fiber. Inside it is a compression, outside fiber is under tension. So near tension zone is this. So green is main steel. Similarly, you look at this figure, you look at this diagram, observe this. So here I will show you the steel in the main diagram. Observe this one. This will be, this green color will be main reinforcement for heel in case of cantilever retaining wall. Why? You can see this. Because this is the top is the tension fiber, bottom is the compression fiber. So it means tension zone is above. So here it is like this. Now if you look at this diagram, heel, this is stretched more. This one is inside, this is compressed. It means the reinforcement is here. So you should understand this one first. Whatever I have shown in green color, those are all main reinforcement in stem, heel, and toe respectively. First you understand this one. Later you bother about other things. Later you bother about other things because in any gate exam or in any interview also they are going to ask this question. You show me the position of main steel in cantilever retaining wall. On what basis I am giving it? Also I told you on what basis I am going to provide, because I am looking at which are the tension fibers, which are the compression fibers. The shape of the cantilever retaining wall after it bends. If at all, if it is not sufficiently strong, it bends like this. So based on this only, I am going to decide the position of main steel. Rest all remaining all is distribution bars. All other places wherever you are giving it is distribution bars. And remember that even though your it should cross, for example, steel in the toe, or for that matter, let us say steel in the heel. Let us say heel steel where it is. Theoretically, it should end here. Theoretically, theoretically it should end here. You may feel it because span is taken only this much. While designing, span is taken only this much. So theoretically it should end here, but development length, this is all extra. It should go inside the stem by this much. Then only fixed action will take place. Otherwise, it will not be fixed. Fixed at the junction is not possible. All these bars should overlap. See here, this toe is see toe also. It is theoretically it is the end point, but the green bar has crossed this toe and it has entered in stem. So all these bars should overlap in this junction. Steel from stem, main steel from stem, main steel from heel, main steel from toe. They should overlap. Then only fixed action is possible. If they do not overlap, it becomes simply supported, entire design will fail. So very important is how you position the reinforcement. How do you make it fixed? How do you make the junction fixed? The only solution is overlap the main reinforcements of toe, heel, and stem. So this is what you need to understand in case of your this one. Okay. So the difference, as I told you, now what is how it in what way this is different? Now, except toe, toe will be again behave in the same way unless small counterfort is provided here. If you see the designs, small counterforts are also possible here. If the this side, if the counterfort is not there, you can see again what will happen. Observe here again it is going to go up like this only because of this pressure. But what will happen to this and this? Stem and heel are no longer cantilever slabs. They are continuous slabs supported on counterforts. How it is, I will show you. Now, the way you design it, I cannot draw this figure. I cannot draw it bends like this or it bends like this. It is not possible to draw. I cannot show how the stem and heel are bending in this particular view. This view will not be able to tell you how the stem will bend, how the heel will bend. Here, in case of cantilever, I have shown it very easily. See this figure, I'll show you where it is. In this figure, if you see this, see in this figure, I'm able to explain how the bending of stem, heel, and toe takes place. With the cross-sectional view only, I'm able to explain this. But in case of counterfort, I cannot explain how the bending takes place. I can explain only toe how it bends because there is no counterfort on this side. Nowadays, counterforts are possible this side if the height is too much. If it is a 10 meter, if the earth to be retained is 10 meters, that time I have to provide counterfort this side also. I have to make this toe also as a continuous slab supported on smaller counterforts. I think it is not there in your syllabus. You are having counterfort only on one side. Now, as counterfort is not here, the action of toe is same whether it is cantilever or counterfort retaining wall. Action of toe remains the same. There is no change here. Only change is in case of stem and heel. As I told you, the way it bends, I cannot show with this diagram. I have to draw an isometric view for that. Now you can see this. How it bends, I try to draw this figure. Let us say this is your, just observe this figure now. Only with the help of this diagram, I am able to explain. So this is your counterfort. It is nothing, just it is a T-beam actually. Counterfort is nothing but a T-beam. How it is T-beam, I will show you later on. It goes like this. It goes like this actually. Now I'll draw one more because I need to draw at least 3 counterforts. Then only it is possible for me to explain what exactly is this, how it behaves. I'll try to draw this like this. You can see this figure. Again, one more I'll show like this. And it goes on like this. Okay. Now you look at this particular, this is what is your counterfort retaining wall. Now what happens here is, this stem is no longer a cantilever slab. It is a slab. It is a continuous slab supported on counterforts. These are all the supports now. So the reinforcement in the counterfort is provided in such a way that it is not going to bend. Now observe this. This side. Now the earth pressure acts like this on the stem. There will be a number of counterforts will be there. Now how it bends, observe this. Because of earth pressure, these are the two supports. You have to imagine a situation like this, which is not easy to imagine actually, but Try to understand in that way. Imagine a situation like this in case of counterforts. I am drawing the stem here. Stem. This is a counterfort. This is a counterfort. These are all counterforts here. Whatever arrow I am showing, those are all counterforts. Now it bends like this, isn't it? If the pressure is like this, simple continuous beam or a slab, I will use a different color. Okay. Now look at two supports and how this beam or a slab bends in between these two supports. Same thing I'm going to show for this support, and this is a vertical slab. Now what will happen here is it bends because of this earth pressure. The these two are trying to hold this one, whereas the earth is acting pressure on this slab, whereas these two counterforts are trying to prevent it. They're trying to prevent this moving away. Because of this earth pressure, it tries to move away now. Stem tries to move away, but whereas these two are trying to hold the stem in position, stem slab in position. Now what happens is, just this is the earth pressure. What happens you see here? This will happen. Again, if you go next, this will happen. Imagine this one more support is there here. Otherwise, you will get confused. One more support is here also. Actually, it is overhanging, but it is extending. I'm telling you. Even this is also like this. It goes. See how it is trying to bend. How the stem slab is trying to bend, but it is prevented by these counterforts which are acting as supports. It means this is a continuous slab supported on counterforts. Simple thing is you have to design a continuous slab. That's all. Nothing is there. Formula, everything is fixed. WL square by 12, WL square by 10. Those expressions are there because at the junction the bending moment is different. At the center of the stem, the bending moment is different. So in this way, the shape of stem, which is acting as a continuous slab supported on counterforts. These counterforts are nothing but T-beams. It is very difficult to imagine a counterfort acting like a T-beam. I'll try to show you. Observe this. I'll try to show you how it is acting as a T-beam. Counterfort is a T-beam. I'm telling how it is. I'll take some part. I'll draw one line like this. On this side also, I'll draw one line. Observe this one. Can you get this T-beam now? Just see this. This is the flange. Web is this. Web is not of uniform. It is triangular web is there now. Now this is a T-beam. I'll show you here. I'll just hatch it and I'll tell you. Which is a T-beam. Observe. This is the flange. This all is flange actually. This is all flange. Now, whatever this wedge is there, not triangular. Triangular is actually it is a T-beam, rib of the T-beam. This is the flange of the T-beam. Rib is different. Whatever you have seen so far. Normally, you may feel that it should have been like this. This is a horizontal line here. Then it ends here only. It ends here only like this. It is a rectangular prism here. If this is a rectangular prism, you will easily appreciate it is a T-beam rib. This is the flange of the T-beam. But only thing that has happened is a triangular portion of the rib is removed. triangular. That is why only a rectangular, I mean triangular wedge has remained here. So in this way, you can imagine this as a T-beam with a with reducing dimension of the rib. Rib is not triangular prism. Rib is a rib is a triangular prism. It is not a rectangular prism. Okay. So in this way, you can understand how this whatever we call it as a counterfort is looking like. So if I now you get see in this figure, you try to understand the T beam as you have seen before. Then in that one you remove some top portion. A triangular wedge is removed. Only triangular wedge is left. This triangular wedge is nothing but it is rib. Flange is as usual. So in this way, this is a T beam. Now your job is to design stem which is continuous slab supported on counterfort. Simple formula is there. Once you know this, everything is simple. Similarly, observe this one here. One more important thing is similarly, a heel also is continuous slab supported on counterforts. This is also going to how it bends. Observe this. Again, it is going to bend like this, like this, because it is trying to stem is trying that is a counterfort is trying to hold this one in position. So wherever counterforts are there, it is trying to hold the slab in position. In between, it is bends like this. In between this counterforts, it bends. It becomes this shape. It bends like this. So this is also continuous slab only. Again, you can see the problem becomes simple. Same formula is used for bending moment calculation. The notes are very simple actually. I'll send the notes. I have the notes here. I'll show you that one. Now the problem is it means uh, you are going to design the stem and heel considering both are continuous slabs supported on counterforts. Now observe here how the steel should be there in counterfort in order to achieve this one. So the steel from the counterfort should go inside like this. Steel from counterfort should go inside like this. Okay, then only it acts as a support for stem as well as heel slab. It means if the earth pressure, weight of the earth pressure trying to, it is acting like this on the heel slab, it is trying to push it down. When the earth pressure is like earth, weight of the earth is acting down like this, it is going to bend like this. Okay, it has to be prevented by the counterfort. That is why the reinforcement are there like this. It means till you design the counterfort, still some doubts will be there in your mind. Like unless the counterfort is designed, last step it is. Counterfort design is over. You'll further you will come back and you will understand how this counterfort is working, how it is trying to prevent, how it acts as a support for both stem slab as well as heel slabs. Both are continuous slabs. Formula, everything is very simple actually. All remaining things are easy. That is why the thickness is uniform because bending moment is not zero at the top, next at the bottom. It is not like that. Bending moment is different now. See this entire mid span, the portion which is in between the counterforts, how it bends. See there. So no question of non-uniform thickness of stem. Thickness of stem has to be uniform in case of counterfort retaining walls. Now I'll start the explanation on counterfort retaining wall design. I'll go fast here. Observe. See, this is the concept you should understand. Basics, fundamental should be clear. Otherwise, you can't do anything in gate exam and all. If you don't know the concept only. So I told you the difference between cantilever and counterfort retaining walls. So let us see this one here. So the notes I prepared first time, then subsequently one student has written this. 2 years back, I gave the notes to one student. My notes, I told him to write it neatly and submit it. Nagaraj, that fellow is working in a very big company right now. This man is working in a very big company. 3 years back, he has completed. So observe this one. Counterfort retaining wall. Design a counterfort retaining wall for the following data. Height of the wall above the ground should be 6 meter. It is more than 5 meter, we can see. In the examination, even if it is given as 5 meters and they are asking you to design counterfort, there is no other choice, you have to design. Height of the wall above the ground, SBC, angle of friction 33 degrees, unit weight of soil, density 16, spacing of counterforts is usually 3 meters. Now almost it is fixed, 3 to 3.5 meters. Best center to center distance is 3 meters. What is that 3 meter is? I think you can follow that one. I told you this one. What is that the spacing between center to center is this series figure. Center to center distance between the counterforts is given like this. So this is one point, this is center. They are separated by 3 meters. Almost it is a worldwide standard, it is 3 to 3.5 meter. It is given, if it not given, you assume it is 3 meters. Now that is given. Adapt M20 and FE415. Still in your question paper, it may be FE500. That you have to be careful. So find the minimum depth. Steps are like this. Depth of foundation you calculate because earth to be retained. See, from the available ground at the site, it is 6 meter. I have to go inside for hard strata. I have to take the heel and toe below the ground level. So minimum depth of foundation is, let us say, 0.869. It is rounded off to 1 meter. Okay. SBC by gamma into Ka square. This is the formula. 1 minus sine phi by 1 plus sine phi square. So 160 is SBC. Density of the soil is 60. So 0.89, 0.869. It is rounded off to 1 meter. So preliminary or tentative dimensions. You have to fix the dimensions. You remember that whether it is a cantilever or counterfort retaining wall, you have to start with some preliminary dimensions, check it for stability. If it fails in the stability, you don't have to go further for RCC design. Try to understand, 20% is not RCC only here. 20% of the solution is not RCC. Because initially you have to check the stability. If it fails in the stability, revise the dimensions, then again check for stability. If it is stable, then you go for RCC design with all bending moment and shear force calculations. Otherwise, you have to, there is no, that is why the design is not unique. Whether it is steel or RCC, there is no unique design. It is always trial and error. Always you may end up with different solutions. There is no unique solution for designs. Solutions vary from one designer to another design. Both will be safe. Maybe somebody may be uneconomical, somebody may be economical, like that. Some dimensions may change or AST may slightly change, but both are considered as correct only by the examiner as long as they satisfy the criteria given in the code books. So here, let us fix the preliminary dimensions. Height of the wall is now height to be retained plus whatever depth I have calculated to 1 meter. So total height is 7 meter. Width of the base of the slab 0.6 h is taken. These are all approximate. We may have to revise also. So 0.6 of 7. Total height is 7 meter. 6 is above the ground, 1 is below the ground, total is 7. Then it is B is equal to 4.2 meter. These are all very simple things. Let us go to the next page. Very simple technique is there. Observe this notes. Then finalize the toe projection. 0.3 times B. Remember not capital H. Whereas I used H there. Here I am going to use toe projection is 0.3 times B. 4.2. So in the previous step 4.2 was calculated. 0.3 times that I am choosing it as 1.26 meter. These are all approximate trial and error. Thumb rules are given. When you use these thumb rules, there will not be any problem. You don't have to revise the design. Whenever thumb rules are used and when you continue 9 out of 10 times, you don't have to revise the design. That is why thumb rules are given. Thickness of stem ds h by 20, 7 by 20.35. Stem thickness is also finalized. Thickness of the base slab h by 12. Very simple things are there to remember. H by 20 because you remember base slab is thicker than stem slab. First thing that you should remember here is base slab, that is heel is thicker than stem. In case of counterfort retaining walls, heel is thicker than stem. Stem is 350. Heel is nearly double that. 600 has taken. 0.58 is rounded off. 580 mm is rounded off to 20 mm is added there, sir. So it is 600 mm. Heel slab projection. How much is the projection? Because B we know it. B is we know it. In that one, toe you remove. Okay. Here and DS you remove. Heel slab projection 4.2 minus 1.26 minus 0.35, which is 2.59 meter. I'll show you in the diagram. Height of the stem HS. Now the stem height you observe here. Stem height we have to calculate H minus dB. So 4.2 is the width. Okay. We are trying to find out, let us say, height of the stem. I want this height. I don't know whether I'm wasting time here, but anyway, just see here. I want the height of the stem, how to get it. How to get this. Height of the stem is, total height is minus thickness of the heel, ds or whatever. In this way, we have to calculate them separately. H minus dB. Base thickness, dB I can call it as base thickness, which is 0.6. So 7 minus 0.6. You can say whatever height they have given in the problem is 6 meters given. Based on this one only, I have calculated all these dimensions. You try to understand. Basically, this 6 meter is used to calculate all these things. It means you have to finalize the preliminary dimensions using height of earth to be retained. Now, what you should observe here is both heel and toe are below the ground. Below the ground because the original ground line was this. Where is the original ground line before the construction? Original ground line is here. See, original ground is here. Six meter was given. From this 6 meter, what I have done, you can see it. So many dimensions are calculated using a simple technique. All these are uniform in thickness initially. Even later also, we are not going to change the thickness if it is a counterfort retaining wall. So anybody has any questions here? 6 meter, then depth was calculated, which is 1 meter, totally 7. From 7, I am able to fix up all these dimensions, projections, everything is done. It is all preliminary. I may have to change the dimensions also if it fails in stability check. I think there is no doubt, is it? Any questions here? All the dimensions are fixed now. All dimensions are fixed. Basically 6 is given. Depth of foundation was calculated, which was rounded off to 1 meter. Totally, I am having 7 meter. From this 7 meter, I am able to fix up all these dimensions. Don't worry about counterfort for the time being. No need to worry about counterfort in the initial stage. Any questions in this one? Another 10 minutes, I'll continue. Another 5 minutes, I'll continue because about to end. Now you can see this one here. It means you don't worry about RCC in the beginning, just finalize the dimensions, check for the stability. If it is satisfies the stability criteria, then only think of designing it RCC. Otherwise, you have to go back and revise it. Now, stability analysis is third step. Forces acting and their moments about the toe edge are tabulated in the below table. So weight of the stem, weight of the base, weight of the backfill. So when I say weight of the base, it means it includes both heel as well as toe. So let us see this one, weight of the stem. Thickness is 350 mm, 0.35, height is 6.4. This has been separately calculated. Capital H, 7 minus base thickness is 6.2. 7 minus 0.6. So it is the cross-sectional dimension into 1 meter is the length of the stem, 25 is the density, 56. 56 kilonewton weight of the stem per meter length. It weighs 56 kilonewton. Then position is 1.26 plus 0.35 by 2. I think you can follow this one, isn't it? Is there any doubt in this? 1.6, 1.26 plus 3.35 by 2 is the perpendicular distance. I think I'll just explain this point. What is this observed here? Now, what is that 1.26 plus 0.35 by 2? I'll just simply draw the diagram. I'll draw this diagram and I'll show you what is that. So this is the centroid of the stem centroid it is. Moment should be taken from this. This is the point where moments are taken. How much is this distance? 1.26 plus 0.35 by 2. So that is what is shown in the next slide. So 1.26 plus 0.35 by 2. So multiply 56 into 1.435. 56 into 1.4 to 80.36. Weight of the base. Directly entire base should be taken. Don't separate a toe and heel here. When stability analysis is done, you take entire weight because it is made up of same material. So cross section dimension is 4.2 into this height, 0.6 cross section dimension into centroid of this rectangle. So centroid of this rectangle is nothing but it is somewhere here, 4.2 by 2. 4.2 by 2, somewhere here it is. This distance, entire rectangle, only 2 rectangles are taken, then weight of backfill should be taken. That is what I have done here. Absolutely, there is no confusion here. Weight of the base is 0.6, thickness 4.2, entire dimension of the base. 1 meter is the length of the base here. 25 is density of concrete, 63. 4.2 by 2 from O. So 132, multiply 63 into 2.2. Similarly, backfill W3. How to find the weight of the backfill? See whatever dimension is there above the heel, that rectangle should be taken for calculation of weight. So 2.59 into 6.4. This is a rectangle actually. This is a rectangle. So this rectangle is nothing but heel, whatever heel is there, no? Size of the this one it is. Okay, I'll show you that one. Into density into 1 meter length of the backfill. Backfill is of 1 meter length only you should take. Per meter length perpendicular to this plane, we have to measure. Now observe this, how it is. You observe this calculation here, how it is done. Now what is backfill? You observe this one. So I'll draw a diagram like this using some other color. This is a rectangle. This is a rectangle. Weight of the backfill is this much of the weight is acting on the heel. What is the weight of this backfill per meter length? So per meter is, if you go perpendicular to the board, this is 1 meter. This is 1 meter. So volume of this, it is nothing but this heel projection into 6.4 is the height of the stem into 1 meter into density. That is what I have done here. You can see this 2.59 is heel projection, height of the stem is 6.4. So that much is the backfill that is standing on the heel into density into 1 meter, that is along the length of the retaining wall. I have to consider only 1 meter. So 20265.216. Now you calculate this distance, perpendicular distance from the same point O. Remaining all is simple actually. Stability analysis has to be done. If the stability analysis is wrong, means again you have to revise everything. So don't commit any mistakes here. For example, if you say that it is unstable, I will revise. If you wrongly do this stability analysis, even though the dimensions are okay, but you have done it wrongly, again you are going back and revising the design. It is going to take a lot of time in the exam. Now observe this one. Whatever this one rectangle I have shown, centered of this rectangle from O, because O is the common point of measurement. Now centered of this is observed. That distance you should understand. Centered is here. Simply it is centered of this rectangle, whatever yellow color I have shown. Yellow color rectangle, and the centered of this rectangle from O, horizontal distance, X coordinate. Get the X coordinate of this centroid. This distance you have to get. How much is this? 1.26 plus 0.35 plus 2.52. 2.4, and how much it is? This by 2. That is, start with this by 2 plus this plus this. That is how you have to calculate the centroid. See this. 2.59 by 2, half of the rectangle, yellow rectangle, plus 1.61. 1.61 is sum of those two. Sum of this and this. That is nothing but 1.62. So finally, you are able to find the centroid from the common points. You can see the column here, position from O. Common point is O. From O only these X coordinates are calculated. X coordinates of centroids are calculated from O only. Then multiply this and this, you will get 17.452. Now add these values, force values, sigma W. This column should be added, all the forces. Add all these M values, moment, bending moment, you will get sigma M. Now overturning moment and all you can calculate it. M naught is equal to P into H by 3. So overturning moment is this. So because of this, there is a overturning of the retaining wall takes place. So pH into H by 3, force into perpendicular distance. Triangular, it is a triangular variation is there. That is why H by 3 is the distance between base and, because centered of the triangle from the base is H by 3. So 1/6 of K gamma H cube. Directly you can remember this formula here. Substitute everything here. 269.645 is the value. Overturning moment. The restoring moment. Restoring moment is related to weight of the entire structure. Restoring moment. See, 0.9 MR. So 0.9, because only 90% is available at the site. That is why 0.9 is taken. Our understanding is 100% restoring moment is not there at the site because of workmanship and quantity. because of workmanship and quantity, quality of the materials and all that, 100% MR is not available at the site. So only 90% is available. So zero point 0.9 MR by M naught. 0.9 times 90% is available at the site. 0.9 into 983.112. What is this 983.112? Sigma M. See this 983.1. Total moment that is acting on the member. So 0.9 times that divided by 269 overturning moment, it is 3.28. It must be more than 1.4. It means there is no question of overturning. Overturning will not take place. The dimensions are sufficiently big, overturning is not possible. Means dimensions are okay. Because the factor of safety is 3.24, whereas permissible limit is 1.4. If it is less than 1.4, what would have happened? If this is less than 1.4, if this value, I have to revise the dimensions. I have to increase the dimensions because now weight is okay. The weight of the entire retaining wall is okay, excluding the weight of the counterfort. If you include that also, the value further increases actually, but that is not considered here. Check against the sliding 0.9 times FR by FH. FR is equal to mu times sigma W. Mu is taken as 0.5 if not given. Mu into total weight. In that table, whatever the sigma W was calculated, no total, that into 0.5, 192. Then the force which is causing the sliding, horizontal force which causes the sliding is this area of the triangle. Area of the triangle. So this is how it is calculated 115.6. Now divide these two numbers. So 192.9 times you have to take again. Complete FR is not possible at the site. 10% allowance is given for imperfect workmanship and quality of materials may not be standard. Because of the 10% is removed, 0.9 FR by FH. 0.9 into 192 by 115, it is 1.496. It is more than 1. Check against excessive pressure. So I will stop it here. I'm going to stop here now. Actually, the remaining things I'll share the notes. You go through that one. You may follow it. Otherwise, I will some other time I'll repeat the remaining portion here. This is check against excessive pressure. Once it is done, if it clears this check also, it clears this check also. Okay. Then only you should start the RCC design part. I'll take the attendance and I'll stop it. I need to take attendance today because we have received the information 90% of the students are not ready to come to the college. They want only online. Now here when you calculate this sigma using this formula, extreme pressures at the extreme edges of the retaining wall, maximum and minimum values you will get 123 is maximum, 59 is minimum. So maximum is checked with SBC. This maximum should be less than SBC. So even 123.36, which is maximum out of these two, maximum minimum values. Okay, similarly, minimum is 59, maximum is 123. Whichever is more, that is maximum is 123. Compare this one with SBC. So this value is less than SBC. Otherwise, you have to redesign. Means you have to revise the dimensions. Now there is no problem because sigma max is less than SBC. Whatever pressure that is occurring at one of the extreme ends is less than SBC. So SBC takes care of this. Sigma max is 123, SBC is more, so there is no problem. So this is how the stability check is done. Only after the stability check is done and it is satisfied, you go for design of step. It's very simple actually. Ultimately, this is a diagram. These are all the counterforts. It is a continuous slab. Calculation of W is important. How you got W is important. I'll just send the notes there. So this calculation is going to be important. Otherwise, formula is everything is same. WL square by 12, WL square by 12. Means 16 and 12 are maximum positive bending moment. At the center, it is WL square by 16. At the support, it is minus WL square by 12. These two values you should remember, formula. It means always moment is maximum at the supports. WL square by 12 is higher than WL square by 16. So when you want to calculate whether the sagging or hogging is more, here hogging is more than sagging moment. So WL square by 12 is higher because W and L are same in both the cases. L is 3 meters, center to center distance between the counterforts. It means that you have to calculate the steel with respect to this value, 22.656 into 1.5. I think I'll just check it for factored moment because these two is sagging is less, hogging is more, but whichever is more for that value, you calculate the steel and provide the reinforcement everywhere like that. Same steel should be provided in the sagging or hogging sections. It means sagging is there, the you have to see where is the tension zone. When hogging is there, where is the tension? In the respective tension zones only have to provide the reinforcement, but the steel calculated is using only one moment. Only 22 point whatever is value higher is there, no, that value should be taken to calculate AST. Same AST should be provided for both sagging and hogging areas, means tension zones. Okay, so this is how the design is done. Same is there for heel also, and toe is designed as we design in case of cantilever retaining wall. There is no change in the design of toe, whether it is cantilever or whether it is counter.